have a great set of speakers here. We're going to get quick, just like lightning intros to their architectures, the things that they built, the dishes that they prepared for us today to do a little tasting. And we're gonna flip through. Unfortunately, this is not in order, so you gotta do a little pattern matching, a little face recognition here. But yeah, Eric, you want to kick us off? I think this guy.
Yeah. Do I use this or do I use this or?
Use the clicker if you like. You can use any of the microphones.
Okay. I'll use this. Everyone can hear me okay? All right. Great. Yeah. All right. Go. My name's Eric Jensen. I'm joined by Jody Hansen. We're both from the Desert Research Institute and presenting on climateengine.org, a set of tools developed with support by Google, the US Bureau of Land Management, and NOAA-NIDIS. And this tool was definitely not developed just by me. We have a team of 11 people at Desert Research Institute and University of California, Merced, who have developed this tool. It started back in 2014, funded through a Google Faculty Research Award awarded to Justin Huntington at Desert Research Institute and launched publicly in 2016. In 2020, we helped to launch the company Climate Engine. I mention this specifically because climateengine.org and climateengine.com are separate organizations. So if you want to learn more, I don't have time in 4 minutes, but we can talk. And just this year, we relaunched climateengine.org with new data sets, new capabilities, and expanded user support. And since we've relaunched, this text may be very small, but we've been amazed to see that 70% of our users are outside of the US, many coming from environmentally rich countries like India, Colombia, Indonesia, and Mexico. And our users are primarily academic, so we really meet research needs. And so Climate Engine is a set of tools that's freely available that sits on top of Google Earth Engine. So we leverage the cloud computing processing and data catalog, and they provide no-code and low-code capabilities for analysis and visualization. Our primary tools are our web app and our API. We're expanding access to the API right now, so if you want to learn more, talk to Jody or me sometime this week. We also make many of our data sets available through the awesome community catalog. And we have over 80 data sets enabled in Climate Engine across climate and hydrology, remote sensing, forecasts, and hazards. Many of those are accessed through the Earth Engine data catalog, but many others are ones that we ingest, convert to cloud-optimized geotiffs, write to Google Cloud buckets, and ingest into Earth Engine. And then on top of each of these data sets, we have scientific computing that can calculate drought indices and other derived indices that we make easy to do in our app with 4 clicks or 10 lines of code in our API, and then return an interactive map in the Google Maps API if you're in the app, or a geotiff in a cloud bucket if you're using the API. And we have many different calculations that we enable, so all of this is applied across all of our data sets. In terms of the architecture, we manage our code in GitHub and then use, for the web app, and then we use GitHub Actions to deploy to App Engine. And then the requests are made to Earth Engine through user forms populated by the users and returned either in the HiCharts API for time series data or the Google Maps API for maps. We have a Firebase authentication system. And then on the API side, we manage our code in much the same way, but here deploy to Cloud Build, which creates containers to deploy to Cloud Run. All of this is containerized and can be deployed to partner cloud projects. We use various Google microservices to manage the API and use the same user API to manage authentication. And I'm probably a few seconds past 4 minutes, and yeah, thanks.
Great. All right, we're gonna do a quick intermission here and get the chairs ready to roll. Who's next? Do we know who's next? Court? All right. Super. I used up my one joke. All right, so as we get configured here, I'm going to just set some expectations. So we're going to hear from this set of folks. Eric gave a great, just prototypical example of what we're going to hear. Hear who they are, hear about their architecture, and hear about the structure of what they've built. We're going to then do kind of I want to do a round table with the folks on stage, hence the chairs, but also would love to have this be kind of a community collaborative thing. I have a set of 20 questions Ben and I came up with of things that we're interested in from the Earth Engine side. Why did you build this way? Which pieces do you use, et cetera? But I would love for you all to get a lot of value out of, applying this to your own problems, your own contexts, and your own services, if you have them today. How you can incorporate and mix Earth Engine pieces into your workflows. These are fun chairs, like director's chairs. All right. Court, do you want to get set up? I don't want to make you compete for attention here. This is challenging. Cool, yeah. We'll give it a couple seconds. How are we doing on time? We're going to have to go pretty quick. I wanted to have a little more time for conversation. But this is, like I said, we're going to be a little fun, a little funky here. And try out a session. All right. Any questions? Comments? Killing time. Help me out here. All right, I think we only need like 7. 10 people? We have 10 people? Oh, I assume we'd stand. Okay. All right. Do you want to compete for attention, Court? I don't want to put you on the spot.
I'm okay doing that. Yeah.
All right.
That's all right.
You want to be extra charismatic, you promise?
I'll do my best.
That'd be great. All right, we're going to roll. Appreciate it.
Okay, a little bit about me. Human being like you. I have amazing allergic reactions. Here's me sampling some of the very rare and unique flora and fauna in Madagascar. This is what it looks like. A lot of people pay money to have lips like that, but not this guy. Blue Ventures is a marine conservation NGO, and they work pretty much all around the equator. Pretty much everywhere that has mangroves, they try to have a presence. They really focus on locally led initiatives. They help, and they basically are support for that. Things like getting access to the land rights, monitoring, helping set up the monitoring, access to finance. And this picture here is a picture of some mangroves. You can see that they're really unique. That's salt water, so the ocean at high tide comes right up to the bottom of the canopy. It looks really weird, actually. And it's incredibly rich with carbon, much more carbon in the mangroves than in the surrounding tropical forests further inland usually. And it's just very, very dense with life. You can't go into the mangroves without killing things with every single step that you take. It's unbelievable. It's a giant anthill full of life. And people that live nearby, they rely on these forests for protection from storms blowing in off the ocean, for fishing, and their livelihoods. The first tool that Blue Ventures made to try and monitor mangroves, because there weren't a lot of things out there for this, is the GEM. This came out in 2020. This is some code editor scripts in Google Earth Engine, and you can see this on GitHub. This really helps with spotting loss, which allows people that live near these mangroves to take action. That gives them access to finance once they can show that their actions are having a positive effect. And this particular image, this is some Landsat imagery here in a false color composite. You can see that the mangroves really pop out in that kind of red edge along the coast there. This is close to where I chewed on something in the woods that I probably shouldn't have. And the reforestation in this region is really inspiring. So this is something that we're trying to do in the future, is get better mapping of reforestation, because those little sprouts just don't show up at 30-meter pixels. But yeah, this area has been a huge amount of reforestation taking place here. One of the reasons I came this week is to talk about a new version of this sort of similar thing. You can imagine, you guys are all familiar with classification and showing the change in time over an area, and doing that through Google Earth Engine. And this is the new thing that I can take most of the credit for this one. All my colleagues built the original version. I just copied their code into an app, but it uses all sorts of googly stuff. It's a native Android app. This is Android Google Maps SDK, and it allows you to store all the imagery and graphs and data from Google Earth Engine right on the phone, so you can go out into the mangroves and pull it up and still view it even without a connection. Uses some stuff on the back end that similar to other things that we've heard about already. Cloud Run for contacting Google Earth Engine, Firebase for authentication, cloud storage for moving files about. And this is really great for the kind of communities that Blue Ventures works in, because people often do not have access to lots of computing resources, electricity, that kind of thing. But every single person almost has a phone. So the phone is a great target for this kind of work. And that's pretty much everything I have to say. There's some links here. You can find these, of course, in the slides later on. And eventually there'll be a link to download that app.
Fantastic. Thank you. All right, Jake, you're up. And thankfully we got the tall chairs. Just don't put anything on the bottom half of the screen. I'll hand this. It's okay. Sure, yeah.
Thank you very much. Have we got speakers' notes?
Great question.
It's okay. Do you know what, I can run through it quickly. We don't probably have the time.
Godspeed.
Perfect. So is that going forward? That's going back. Perfect. Okay. So from proof of concept to enterprise architecture, so rather than focusing specifically on what Earth kind of looks like, really down to the nitty-gritty, we're going to focus as time has grown, what technologies we've looked at. And this has really been my job at Earth for the last 3 years. So this is Earth so we're a horizontal geospatial tool. We focus kind of many verticals, but key specialisms in nature-based solutions, TNFD, TCFD. We're often operating in like a pretty tight regulatory framework, so we're working really hard on that. And so this is what Earth looked like when I first joined about 3.5 years ago. We were an incredibly simple application, so it's HTML and JavaScript on that front end, going to App Engine, and then going to Earth Engine. And this was really a monolith architecture, if people are familiar with that term. And there was kind of two main drawbacks to that. Monolith meaning that anything we update means we have to then update everything. And so that was a bit of a pain, especially as we were a growing development team. And then secondly, we wanted more concurrency and more scalability. And so that's why we transitioned to this. And this was my first job at Earth. It was building a microservice architecture and moving to something that's a bit more scalable. So immediately you'll see we've moved on the front end to a Vue framework that's similar to React, if anyone's familiar with it. Firebase and Restor for our hosting and database responsibilities. And then we're moving to a microservices architecture. So we're running with lots of cloud functions for business logic, and then for the more advanced use cases, using Cloud Run. And I think the key bit that I want to talk about here is that microservices for us was a game changer in terms of how quickly we could build rapidly. So building a cloud function, if you're quick enough, can take like less than a day. It's incredible to build quickly and incredibly valuable. And one thing, a little tidbit, is I'd say have a look at Functions Framework. That's a great software tool for emulating locally, really helpful as a developer. And finally, as we're kind of approaching maturity, product market fit, and working with more enterprise customers, they're looking for more ways to interact with the platform. It's not just our UI, and that's where the API is needed. And so we're now moving towards the kind of concept of a single point of access for our API. And so that's both the website and other external users using the API, and really understand the concept of drinking our own champagne. So we should be using our own API as well. And so to do that, we've kind of moved to use some more mature technologies, essentially. So that's Cloud Armor, Cloud Load Balancing, and Identity-Aware Proxy to kind of enable scaling, to enable security, and to handle authentication for us in an easier way, so we don't have to worry about all the different kind of authentication methods. And so, yeah, I think that's everything. Oh, so Fast API is another thing, great tool, building APIs super quickly, really valuable. And I think that covers pretty much everything. Thank you very much.
Fabulous. Excellent. All right. Next up, we have William, who really dug into the theme here.
Yeah, so I really tried to milk this buffet and food analogy as far as I could. And I'm bringing to you today an architecture smorgasbord, as we would pronounce it in English, but in fact it would be smörgåsbord in Swedish. And it'll just be me with my broken Swedish today, and not the Swedish waitresses, unfortunately. Maybe next time. We're an early stage startup called Epoch, and we work on land-based supply chains decarbonization. So that's, keep that use case in mind. What do we typically want to do is process large areas, so sourcing regions, supply sheds on an annual basis, derive a lot of biophysical indicators that we can then sort of play around and bounce around between raster, vector, do our own segmentation, use supply provided polygons, and that's sort of the realm, or let's say our sort of loose high-level requirements we have to work with. So that was just, sorry about that. So a bunch of blocks that, that we have to sort of consider. Earth Engine is great for us because we can do some raster heavy lifting, a lot of functionalities that are blocked by HS, but not so important. Like I mentioned, the raster vector interface is very important for us. We need like a lot of capabilities. We don't want to be blocked by a certain technological choice, and that's something to really keep in mind. And finally, working with basically vector management and having a way to keep track and have basically a good database or structured database functionalities to be able to monitor plot locations over time in terms of emissions accounting. So how does it look like now? This is nascent work. The company is barely 4 months old. So this is all very, very recent, but I think there's been a lot of work on the sort of the cloud geography and like from the Google Earth Engine engineers to push some, let's say, canvases and solutions out there that we can sort of repackage and reuse to our use case. So important component, top left, just heavy lifting of the raster processing, like I said, out to the Earth Engine, indexing back with cloud functions, probably something that some of you are already doing. Then for the heavier processes, cloud workflows, and data flow, using the high volume APIs, also been presented at some of the sessions. Then from data flow to BigQuery to store these plot level objects. And then what's interesting now is once we're into BigQuery, then how do we sort of make sure it's a two-way street back to raster information? And then we have some nice HTTP triggers that we can use that have also been provided by Earth Engine engineers. But now the fun part is, what do each of these components cost in relative terms? Of course, I'm not going to go into exact numbers because it's probably not that relevant for you, but I thought that might be interesting just to kind of see, including the front end and the sort of the requests and the reads into Earth Engine and how much that costs. So, of course, heavy lifting of the Earth Engine, expensive. And what was a surprise to me is also the dynamic raster, dynamic tile endpoints from GetMap are also pretty pricey. And yeah, so maybe that's an overview that I'd love to discuss today. Wanted to bring a bit of money into the conversation today. And yeah, that's it for me.
Thank you, William. Thank you. Next up is Olga. You're gonna go around. Good call.
All right. Yes. Hi everyone. So I'm from Restor. I'm technical product manager, Olga. And Restor, I have a link, which I don't know if you can see under the chairs, but it's restor.eco. So if you want to know how fast things work and what we have there, you can use your laptops to open the webpage, and I will point to a couple of the things. But mostly today, I will talk about how we implement it and why things work fast and how some things just work slow. So this is our platform. We are a non-profit startup. We are focusing on restoration conservation organizations all over the world. So there is a big barrier. So you may be a great implementer on the ground, but you may not have all the skills of GIS that everyone else here in the room would have. So you may want to pull the data about ecoregions or the data about tree cover, lost tree cover potential for the particular site that you are on. You may not know how to do that. For us, it would be 5 minutes, 5 lines of code, and you get all the computations, but there is a big gap between the implementers on the ground and the science that is in the scientific papers and all the calculations they do. So all the sites we are, so 2 things for those who actually open our website. There is on this toolbar, this is not the newest, should be a draw polygon, so you can have on-the-fly calculations and you will see how fast things work with the Earth Engine. And if you click on any of the sites, you will see some scientific data that comes from the Earth Engine. Restor currently has 135,000 natural sites all across the world and 1,500 more organizations on the platform working in this space. In 140 countries, and our platform in 7 languages, localizations, and all other topics. If anyone has challenges about that, happy to talk afterwards, but we talk about geospatial. Funny to say, the platform, how it looks now, didn't look always like that. Our MVP was actually Earth Engine app, which was tailored for every single user organizations that we were working with. So in order to figure out which datasets we want to build and how we can bring value, we had this complex, many lines of code Earth Engine app, which is the fastest way for you to put the prototype and talk to your users before you start investing into developing anything. And even if you develop already something, testing new ideas, and before you start implementing, that can be half an hour, you can put together some really great stuff. Now, that's how it looks now. So if I go back, that's the same site. It looks prettier. You can upload photos. You can have nice icons. We have beautiful designers who work on all these visualizations. You can see a lot of some of the scientific data pooled. It's different data layers. This data set is interesting, can talk separately about that, about species list, which uses 27,000 raster images to do some of the calculations. So there are some things that we had to do it faster. But I'm here to talk about architecture, so very, very quickly. We use 2 service accounts for the on-the-fly calculation. So when you draw a polygon and the numbers are pooled, this is separate queue and separate way to talk to the Earth Engine. And then batch processing, where we do some logic on how to package those polygons and make it. So this is a front end. We have all these microservices. Like, I would not surprise you about this architecture. We have a messaging system. It's Kafka bus. So we put each of the microservices, if they want something, they put message in the queue, create event, we read events, and so on. And the thing that interacts with the Earth Engine are Earth Engine integration. This is basically a catalog of different calculations. And so eProxy is the front end, and to talk to integration. So eProxy is a gateway for Restor front end and for on-fly calculations and for the triggering, like batch processing. Now, batch processing. eProxy puts together. So it doesn't submit every task. It collects. So let's say there's 2 scenarios. You come on the website, draw a polygon. We very quickly deliver the results, show you area of interest, get you very, very excited. You come as organizations and you bring 10,000 very complex polygons with different complex shapes, and you want your results immediately. You would need a little bit to wait. What the proxy would be doing, it would be implementing some logic based on the vertices of your polygons. It would split into the smaller tasks and submit different batches that we will later store in the database, and you will have the data available. So that's very simple, talking about how our architecture looks like. You can go explore sites, organizations, and collections on the platform, but in the nutshell, that's what we do. That's Restor. Happy to talk more afterwards.
Super. Jonathan, you're on. Ooh, shortcut. Double shortcut. Excellent. Good to go.
Great. Awesome. Hi, everyone. My name is Jonathan Pandolcon. I'm the visiting assistant professor of GIS at Clark University. I had a shameless plug for our MS GIS program, but I think the chairs are going to muddy that a little bit. My dissertation work was at UCLA Geography, partly funded by the County of Los Angeles, which is why I'm here today. LA County Department of Public Health was interested in using remote sensing to help optimize the planning and management of its urban forest. Specifically, they were looking at their public street trees, and with a lot of aggressive planning programs in place around the world, they wanted to make sure they're planting the right species in the right place for the right reasons. And so this is where I came in. I developed a random forest model using over 16,000 training data provided by the county. We did this in Google Earth Engine, and so this is classifying public trees. Now, as the project evolved, another question arose where our stakeholders were asking, well, can we also do private trees? Now, because we didn't have any training data for privately grown trees, there was a certain method that we were interested in looking at using computer vision, but it was using 3D data, so we did it in Google Cloud instead of Earth Engine. This work is still ongoing, and I'll continue at Clark University. So here to talk about architecture, first, the random forest model. Because we're working with three-dimensional discrete return LiDAR provided by the county, collected by the county, we did this all local using R. Didn't want to pay for any cloud storage, didn't have the budget. I was just a PhD student. But once we had those data derivatives, we could then begin layer stacking with optical data hosted on Earth Engine. And this was the main appeal to using Earth Engine, is that the data is already there. We can do all this stacking. We can build a random forest model, run a k-fold cross-validation, and get some results. Now, these results were most useful to our stakeholders so that they could see where these species are, what crowns were classified as what species, and then run some time series analysis and track the condition, measure and monitor how these species are doing in certain areas around. Now, we developed this into a public-facing app. However, a lot of our stakeholders have existing sort of architectures of their own. It's a public entity. Almighty Esri has a lot of enterprise licenses, so sometimes our stakeholders just want the data. So we provided a data export at an earlier part in our model. Now, the architecture for computer vision follows a very similar track. Again, a lot of local processing using R for LiDAR data. But because we preserve the three-dimensionality of that data, we actually bring it into Google Cloud. We can then fuse that with optical data that's been exported as a cloud asset from Earth Engine, fuse that together. We trained our computer vision model, got our results, same thing, plug it into an app, or provide a GIS layer earlier on. Now, what exactly does the app offer? Species locations, crown metrics, charts, tables, time series NDVI, tracking, or using any other sort of index that you might be interested in to track the condition of a specific tree or species. And this is an ongoing process. We owe a 100-page final report at the end of this calendar year. And if anyone knows, I'm just a lowly person working on one app by myself, following up some really great organizations. But as you can imagine, iterative process working with clients and stakeholders. So this is continuing and ongoing. This is what we'll continue to work with LA County with. And again, as I mentioned, fine-tuning our computer vision model to increase our accuracies. Thank you.
You're up again. All right. Now we've got Vivian. Any way you want to do it. You're there.
It's very challenging.
It's not easy.
No, it's 1.56 centimeters high, so it's not exactly great. So thank you, everybody, for coming to this presentation today. I'm going to talk a little bit about Trase Spatial, which is the next frontier for Trase. But first, let me introduce Trase. So Trase maps supply chain. So what we do is basically a data-driven transparency that enable people to understand where commodities, agricultural commodities, that are linked to 70% of deforestation in tropical areas, where they are going. So we map not only the place of production, but also importers and exporters, and the country of import. It looks a little bit like that, but you can see that we have these 4 different columns, also, which means that we present the municipality of production, the 2 different companies, exporters and importers, but also the economic block, which actually provides us 2 different perspectives. So you have the perspective of the country of import, the economic block, and the governments, and you also have the perspective of the producers, which gives us a little bit more intentions around the spatial data. And this is extremely interesting for us to understand how supply sheds, which are this not only a combination of different jurisdictions, but also different farms, for example, they relate to facilities like silos, refineries, crushing facilities, or mills, and then we can really understand the dynamic of it. We do that with quite a lot of spatial data. Well, the first and the second trace phase was a little bit like that. So we used an RGE API to not only ingest some raster files that wasn't there already, and to process that in Google Earth Engine to understand what are the impacts of those commodities in the place of production. We also merged that together with the trace flow, so you need to understand a little bit the configuration of the team to understand why we do that. So we have a team that is specialized in understanding the flows, to map the trade flows, and a team that is specialized in the metrics, in the impact metrics, like CO2 emissions or deforestation. And they meet in this runbook that is just a combination of different scripts to merge this information and then make it available in this apparently invisible database. Oh, it's here. Interesting. So one interesting thing is, because we are quite a big team, we're around 55 people, some of them full-time located, but also we are collaborating with a lot of different organizations. We need to give a lot of flexibility, not only in the programming language, but also in how they're going to deliver this. So at the end of the day, what we try to do with this runbook is to merge this information. But look, the database again. But what we do for the spatial data is something completely different. Let me just bring the database. OK, there you go. And I love it to see the presentation from Restor, because it feels like we are going towards the same direction. We try to implement the Google Earth Engine app to understand what we can do with the spatial data that we have. It looks a little bit like this, the first version of it, to try to show people how we calculate the deforestation that is connected to the production, and how this can be allocated not only to companies, but also to countries that are purchasing these commodities. Of course, using Google Earth Engine the apps are completely amazing. It's easy to build. You can do something that is fit for purpose. However, it's still demand a little bit more training for the rest of the team. The front end is limited in terms of customization, and some feature selections and chart generation can be really hard to implement, especially when you're doing a lot of kind of like heavy stuff, selecting features. And that's why we're now producing testing, actually. We're in the phase of testing a more solid and stable product. I must say that I'm completely in love of Flutter and Dart, because we have an app in Brazil with these 2 technologies. However, it's not exactly stable, and that's why we're still looking for React. But one thing that we heard, I think was yesterday, was this integration between big data, BigQuery, and the Google Earth Engine, and this is completely amazing, brings a lot of efficiency, also because we can have the trade flows there and do all this machinery of merging impacts in the trade flows, and then offer this through a React environment for people to really interact with this data. It's going to look a little bit like the possibility of selecting some companies and see exactly the configuration of their supply sheds, just like you can see some risks associated, and it's going to be probably very interesting for people trying to manage risk, facing, for example, the European legislation right now, the European deforestation regulation. So that's it. Thank you very much.
All right, let's do another round of applause just for everybody while folks walk up. Let's get our speakers on stage here. If you were wondering what the chairs were for. All right, we've got 15-ish minutes on the clock. Oh, very nice touch, Ben.
Yeah. So we have 10 chairs. I don't know if you want to sit down.
Okay, I'm going to deputize some people just kind of in the middle. Okay. This is an open session. I have some questions for folks. I'm curious. I'm going to start with an easy one. Like how I saw a mix of Python, Earth Engine client usage, JavaScript client usage, and R, which is pretty cool. And I'm curious if anybody, how you chose those, and if anybody uses anything different. REST API in the mix in any part of that. Maybe we raise our hands to get microphones.
Yeah, so I can speak to Blox. We're pretty much 100% Python. We briefly used the Node.js version maybe 2 years ago for the kind of asset management, but we moved to using the REST API for that, just because it meant less dependencies, lighter weight deployment sort of thing.
I just want to talk a little bit more about the usage of R. So one thing that we try to respect as much as we can is the culture behind of how you solve your things, right? So because we have such kind of like diverse type of teams, we have different teams working in different organizations, we don't want to impose anything for them, and we want to be just the ones responsible to just consolidate the product. So respecting that people can access R, now sometimes enabling them to do that, for example, with the RGE, which is to use the API to access Google Earth Engine, is really increasing the speed of the process because people, I don't know, that maybe that's a feeling. I would love to hear a little bit of reaction on that. But my feeling is that the R people, usually they underestimate the power of R because they feel more kind of like researchers, but not exactly developers. And it's really good to kind of like break this barrier a little bit.
Any other comments? All right, I'm curious. Are there ways that we can make the client libraries easier to access? So we publish the Python client, we publish the JavaScript client. Is there other stuff that you'd want us to package up? Would a Go client help? Would a C++ client help?
I would love to have a Go client. I considered writing one for my project because Go has an excellent concurrency story, whereas Python and JavaScript not so much. And when you're making lots of requests, you put them in parallel, it all gets done a lot faster. And Go is very simple language, easy to learn. It's fantastic. So yeah, I would love to see that.
Anyone else for Go?
I mean, it's not so much about what other languages should be supported through client access, but more just interface in general. Like there's this new feature view data structure, I guess, which are essentially vector tiles. Any way we could sort of access those through an external application, which is not the Earth Engine, that's probably what probably other people have been thinking the same. But yeah,
I see a thumbs up. Other folks share that? Yeah, I see nods. I'm curious. So that's a nice transition. Thank you. Into other like data formats. I'd love to know if there are ways that we could make the surface of Earth Engine more friendly in terms of what we produce for your applications. Is there any way we could simplify some of those beautiful diagrams up there?
You've touched a sore spot for me. So we bring in quite a bit of vector formats for multiple clients. And at the moment, Earth Engine actually only supports shapefile import. And so at the moment, I'm a lot of the time maintaining a importer for various types of vector format. And that's definitely a sore point for me at the moment as the software engineer.
What types?
So I'm trying to think. So shapefiles of projections that aren't supported in Earth Engine at the moment. GeoJSON when it's larger than 10 megabytes. And then GeoParquet. I'm trying to think the other vector formats. KML, KMZ, that sort of stuff.
GeoPackage?
Yes. I don't actually know if we've got GeoPackage support.
Okay. Yes, I see confirmation and head nods. Go ahead. Yeah.
Maybe one, we can add images to image collection. I cannot add features to feature collection, or maybe I missed something. You need to re-export all the feature collection. That's why we're mostly using Earth Engine to get data out and not like running things within the Earth Engine, and there's a lot of interaction basically out instead of both direction.
So mutable feature collections that can change, feature collections that can add to. I love the agreement here. Everybody, send some emails to the team. We'll prioritize things. Yeah, go ahead.
We also struggle with vector data visualization in Earth Engine and are exploring feature views as an option for displaying some of that using the vector tile service. But needing to write those files out is often a blocker. And because we use the Google Maps API, we're a little bit more limited in terms of the types of rendering we can do on the fly. So that's become kind of a pinch point where we could do choropleth mapping and do some of this more advanced mapping over areas of interest, but trying to figure out ways to do that. So yeah, always interested in creative solutions for that too.
Can I dig a bit into, you mentioned that it's difficult to export the data or difficult to concretize the data, export it as an asset. Did I hear that right?
It's straightforward to export it, but being able to produce on-the-fly feature views,
Gotcha.
where we can take user requests through forms and then be able to render the data on the fly is, yeah.
Very
We
nice.
have the back end kind of set up to do that in Earth Engine, but yeah, struggle to get the feature view objects. So.
Cool. I mean, not cool that you struggle, but cool feedback. So I can keep asking questions. Do folks in the audience have questions? You can raise your hand and I'll, yes, all right. I'll need that microphone back. What? Oh, we have another one right there? Perfect. Appreciate it. That's Richard.
Yeah, this is a question for everybody. Since most of you are like a startup, I would like to learn more about computing cost. And in the process, if you switch your workflow and you moved, or I think that would be great if you hear from you. Thanks.
I guess since I'm the one that started talking about moneying, I won't say complaining, but I mean, in the current situation with the pricing that I'm facing with the application, we're going to definitely build a hybrid setup where we use sort of more like open source, traditional geospatial Python like infrastructure, especially like accessing, for example, of creating like dynamic tile endpoints. Definitely going to do that directly from the cloud storage assets or rasters, cogs, as opposed to going through the Earth Engine for that. Because yeah, we've just seen in some parts of the architecture flow that yeah, it's more expensive. Some operations are more expensive than I initially thought, and it's of course pricing is always a bit of a, let's say, esoteric thing. It's really hard to know, and you know, it's even though cloud services and cloud computing is quite old by now. There's always a bit of sort of myth around how costs build up based on usage. So yeah, I think we're going to go forward with a hybrid. Just stay flexible in how you design your application. Yeah, and make sure that what you can do outside of Earth Engine, do it outside of Earth Engine, and what is so convenient to do in Earth Engine, then do it in Earth Engine. So for example, what I call the raster heavy lifting, like all this time series, like pixel tensor processing it's so valuable to do it in Earth Engine that I wouldn't really consider moving that out. But I think a lot of the piping around, you can be a bit more, sort of a bit more flexible and sort of go back to some alternative. Yeah.
Can I ask real quick, how do you keep track? How do you organize how do you track which pieces cost which amount? I'm fascinated by that slide. I love it. What tools do you use for that?
Not really a tool at this point. It's more sort of piecewise. As I was building it, I basically had an AOI of about 30,000 square kilometers, ran it through the entire sort of back-end process, started using it in the React front-end sort of regular usage, like creating these dynamic tile endpoints. And I've just, sort of day by day just looked at the billing, the cost breakdown, just seeing which cost was incurred under which service line.
Okay.
So yeah, it's nothing super elaborate, but yeah, at least I was still able to isolate different operations because it just sort of day by day as I was developing it, I could see the sort of the profile. Yeah.
Okay, so tracking it over time in billing. Would you mind passing it down to Vivian? And while you do, Jody, you look like you had something to say.
Yeah, I was just going to add to that. Especially when you're first starting out, there is a recommended Google hierarchy. And so it talks about having an organization, folders, and projects. So separating things out and like microservices maybe per project is also an excellent way of tracking billing because it is very difficult to sometimes, I mean, I always cross my fingers when I add a new feature because I try to find what it costs, but I never really know. So if you can track the billing and kind of fine tune it by having that structure, that will really help.
I think the only thing I would like to add is I'm gonna state the obvious here. It's kind of like try to understand what really needs to be requested all the time, and what can be a little bit of tabular gymnastic that you can do to reduce the processing capacity, really decrease the necessity of processing things all the time, and this really increases the cost at the point that we evaluated that if we are non-profit, but if we were paying for that, it would be 70% of the cost. But another thing actually is the previous question that we were talking about improvements. We are completely in love with Dataplex and how we can really increase data governance there. And it would be really amazing to see Google Earth Engine more included in this capacity to track not only data sets, but also the pipeline that we use. It's a really fantastic product.
Awesome. We only have like a couple minutes left. I would love to talk about performance. How do you all make things fast? Are they fast? If they are, how'd you make them that way?
I think this ties in quite well to costing as well, actually, performance and costing. And for both of those, we actually have a pretty similar approach where workload tags is something that we use pretty extensively throughout the application to check for a particular workflow that's been run, the actual cost associated with that. And then we're doing some other stuff behind the scenes to kind of track maybe specific sub-functions that are being called inside Earthblocks that are actually costing a lot, or maybe have either a high compute cost or a high memory cost. And then we can kind of track down actually the specific stuff that's happening with the profiler. There is a little hidden profiler in the Python package for Earth Engine that you can use to track that down. And I'd recommend people use it. And it might be something actually it would be worth talking to you about afterwards because we've got a custom version. So it might be a look.
It's no longer hidden. I had a documentation a couple months ago. It's in Python. It's great.
Yes. Yeah, it's great. I'd recommend it.
Anyone else on performance?
My situation's a little different because I'm focused on the mobile app, but caching, saving it all. Don't regenerate the same thing twice if you don't have to. And when you use the app on the phone, everything that Google Earth produces is saved. So you never, essentially for a certain region of interest that you've plotted out in the app, you never make the same request twice. That's true in every domain that you'll write code, and caching is always the secret sauce. That said, one thing I've noticed with some of the stuff that I've done on the back end for that app is we'll do things like we'll want to do the classification and the dynamics and the mapping and like all in one request, essentially. Do it all at once because we've sort of skipped ahead in the process at some point in the app, and we just want to get to the end goal. And maybe when you generate that stuff, it can take a few minutes, and then there may be ways that you want to sort of parse it and chop it up and display certain pieces of information about it. And obviously, you don't want to regenerate it every time you have a question to ask. And the way the client libraries work, as you sort of build up your data structure locally in the client, it's just it's all lazily computated, and it doesn't actually run in Google Earth Engine until you ask for the data back from Google Earth Engine. So one thing I've noticed is if you just put it all into some server-side object, everything you want, and just be like, give me the whole thing, and it'll be really smart, and it won't regenerate the same thing twice. It has some way internally on the back end, I think, just from my experimentation of keeping those objects around for the life cycle of the whole request.
Super. We're going to go a little over time. I'm going to steal like just 2 minutes. Anybody else want to respond to the performance question?
I have a very simple thing. Also think how you design your front end, because the users show up to maybe see, you have 30 beautiful numbers and graphs you want to calculate on the fly. But if you think a little bit of what your users comes in the first place to show, you can pull these numbers faster. So instead of waiting 30 seconds for all the calculations to pull, you can wait 3 seconds and have some of the calculations and split it up so you can integrate that, basically compensate for the limitations on how fast certain things take by designing it smarter on the front end.
Super. I have one last question. So loved seeing the Earth Engine apps that, the early prototypes, the apps that graduated into full applications. What was that point? And for folks who maybe didn't go through that process, why not an Earth Engine app? This is feedback for the team and feedback for other folks who are in the process of building things.
You can go first, I go second.
So those two things were actually in parallel. So we knew that Earth Engine app will not have enough capacity for all the complexity that we want. We want to have organization entities. We want to have authentications, all the different things and different flows. So we were developing Restor already, some basic functionality, while we also wanted to onboard the users already. And you cannot onboard the users on the thing that doesn't exist yet, that you are cooking in the kitchen. So essentially, that was running in the parallel, but it was also a good use case for testing, getting user excited, getting their feedback, and having them being involved in the process of the designing app and figure out what kind of problems and questions we can help them to answer. So also developing geospatial platforms and applications. Those are sometimes very complex projects because you want to work, you want to have an engineering team and you want them to know how to work with this complex data. This is not as easy as just putting the websites together. So so development was taking just longer, but those were in parallel processes. So would recommend to start with the Earth Engine apps if you're starting with the startup ideas.
Well, I have the same recommendation. I think the best thing for us was to be able to isolate the hypothesis that we wanted to really test. And that was the case that we built actually probably 5 or 6 different Google Earth Engine apps. And we found a little bit hard to integrate all of them in one. So it was way easier to build easier Earth Engine apps, simple ones to test a specific hypothesis. I must say that the download function was a game changer because that was the hypothesis that we always test. Like people at the end, they don't want APIs, they want a CSV. And I was kind of it was so much easier for people to access the information. But when we tried to really consolidate the product in one thing, it became really complex. That it was better to just access different libraries and different resources. So that was mainly the case. We thought about just aggregating all of them and kind of you have a website and then you have all these applications that are serving specific specific purpose. But during the user testing, we actually faced the reality that people were looking for something integrated, which is a little bit controversial because every time that we offer something that is more complex, we lose the user. So, I'm not going to go to this crazy thing of user testing, but starting from Google Earth Engine is definitely the right decision.
Can I just add to that? Because there might be one person in the audience who has startup idea and trying to pull some demo using Earth Engine app. At some point when you talk to the users and have different versions, you would have 100 different apps, same apps with the same code, just different underlying data. As you saw the polygons as you onboard the users, you can also have URL, smart URL, and parse that into the same app. So depending on with which URL the user would come, they would see the different stuff in the app. So you would not end up with 1,000 apps in your editor.
Yeah, for us, there were a couple of reasons. The first was Earth Engine apps didn't exist back in 2014, so that wasn't really an option. Also, some of the same reasons that Olga mentioned previously, but we do use Earth Engine apps quite a bit to test out new functionality we're considering adding, new calculations, things like that, just to get a feel for what types of things can be done on the fly and how we might write that Earth Engine code to add to the app. So even for us, just being able to develop out some code that we might use, or maybe we'll just throw away, having that rapid prototyping and just being able to test stuff out is really handy.
Excellent. Super helpful. I know we're over time. I appreciate, our speakers' contributions here. You all have been fabulous. The audience also, thank you for your patience as we have endured a journey together with the chairs. I think we should wrap it up, but definitely I'm going to give you all homework. These people are going to have questions, so find them, ask them questions, chit-chat with them. Thank you all. This has been fun, if chaotic.